Swayam Prabha. Digital India. Educated India.
Okay, good morning. So I have uploaded a tutorial problem sheet in Moodle as tutorial 5. This would involve absorption calculation for concentrated mixtures. Okay, there are 4 problems. 2 of them are tray column design, the first one and second one, and the other 2 are packet column design. In the tray column, I already solved one of the questions. I think I solved this question, the carbon disulfide separation problem. This was solved in the last class, and the first problem would be practice for you. Okay, follow the steps that we did in the problem CS2 problem, and do the same thing for problem 1. The final answer for each question actually is given here. Okay, so this is for you to cross check if the answers are right. Okay, you may not get the exact numbers like this, but in the right ballpark. And in today's class, I'll be talking about design of packed column absorption for a concentrated mixture. This we have not done before. Okay, so this also has 2 questions, problem 3 and 4. Okay, I will do problem 3 in the class today, and problem 4 is for your practice. Okay, so if you know how to solve problem 3, problem 4 should be straightforward. And subsequently, there are some additional questions. These are questions taken from GATE question papers. These questions are much simpler than what we are going to do in the first 4 questions, right? So because these are typically GATE question, numerical question that requires a little bit of effort, but in terms of calculation, they are not that difficult. Okay, so this is for you to practice. So I think we have got about 7 questions or so here. So I kind of urge you to go through all of them and try to solve this by yourself. Well, actually, there are about 9 questions. Okay, so with that, let's take a look at this problem number 3 and solve it in this class. So if you see problem number 3, it says design a tower packed with 50 mm or 2-inch ceramic Rashik rings for the carbon disulfide scrubber of problem 2. The problem we did in the last class, the same problem we are going to do for packed bed. The problem 2 we did in last class was on a tray column design, finding the number of equilibrium trays, efficiency, number of real trays, so and so. Now the same problem of separation of CS2 from nitrogen is to be done in a packet tower, and the packing material is given here, and other things involve assume isothermal operation and a liquid gas ratio of 1.5 times the minimum. Same thing we used in problem 3 also, and a gas pressure drop not exceeding 0.4 inches of H2O per feet of packing, and then use interfacial area A to be 60 meter square by meter cube. So the questions to be answered is are the determine the tower diameter and using average flow rates. So here it's a concentrated mixture, or if it's a concentrated mixture, you would consider the flow rates at the top and bottom and take an average. And then also fluid properties, compute the mass transfer coefficient FGA and FLA and height transfer units HTG, HTL and HTOG. We have not done these problems before. Okay, so that's the reason why we are doing this now. And then compute NTG and with HTG the packing height, and then compute NTOG and corresponding packing height using analytical and graphical methods. So kind of a all-in-one kind of a question, involves pressure drop calculations as well as the height of the packing analytical methods. Also involving local NTOG, NTG and HTG, also overall NTOG and HTOG. So it's kind of all in one pack. So what I will not do is this part I will not do because this is something that we have done enough times. I have got that done in my notes, but in this class I will not show. I will take only the tower diameter calculated from this. Okay, we will do this part B. Okay, this is a new things, and then part D I will do. Part C is a little bit quite involved. So if the time permits, I will also talk about part C. So the way we will do is first part B, then part D, and then if time permits, part C. Now there are some data given here because this involves calculation of mass transfer coefficients. So we have to use some correlations. So it says that for Raschig ring and Burl saddles, the gas phase coefficient is given by some correlations. So what you see here, you see Fg, that is the local gas phase mass transfer coefficient, F type, and then you have got Schmidt number of the gas side. Okay, and it is defined as rho by mu d using all gas properties. And then you have got this G, which is the gas molar flux in the units of kilomole per meter square per second. On the right hand side, you have this parameter ds, which is defined as the diameter of a sphere of the same surface as a single packing material. So this is something we can obtain from tables because we know about the characteristic of the packing material. It's a 50 mm Raschig ring ceramic. And then G prime, gas mass flux. So the difference between G and G prime is G is in molar flux, G prime is in mass flux. Okay, this is in kilomole per meter square second. G prime is in kilogram per meter square per second. This is viscosity of the gas, mu G, and then you've got epsilon L naught. Okay, so epsilon L naught is defined as the operating void spacing in the packing. So you see this is a packed column. So the entire volume will be occupied by the voids as well as by the packing. Only those void spaces are available for the gas to flow. Okay, so this epsilon here is the porosity of the bed under dry conditions where there's no liquid flowing in. But when the liquid is also flowing in, the liquid also will occupy some holdup. So this is the correction for the liquid holdup. Okay, so the effective porosity for the gas to flow, okay, will be the liquid to flow would be the total porosity minus the liquid holdup. So these values are given to you. So epsilon based on the packing material, we can read it from the tables. Calculation of the liquid holdup is a little bit tricky. This involves another 4 equations. So what I did, I calculated that for you and I've given the number here. Okay, generally this will be little smaller compared to the porosity. So even if you ignore phi here, you're not too far off. Okay, but still for this problem, this is being calculated for you given. So that means in this equation, you can get Fg the moment you know what is G and G prime. This G and G prime is something we can calculate because we already have done in problem 2 about the gas flow rates, liquid flow rates, all that we know. Okay, so essentially it's more like a substituting and then making sure that you get the correct number. So this is about getting Fg. If I know Fg, then I can find HTG. Okay, now about the liquid side, again there is another correlation given. Here instead of FL, the local F type mass transfer coefficient, KL is given. This is a K type mass transfer coefficient. So first we have to get KL from this expression and then relate this to FL. So this also involves certain fluid properties as well as the packing material properties. For example, ds, as I said before, it is an effective diameter of a sphere equivalent to the packing material surface area. dl is the diffusion coefficient of the solute in the liquid. So you see, if you hear, we talked about diffusion coefficient of the solute in the gas phase. This is the same solute but diffusing in the liquid, that's dl. And L prime here is the liquid mass flux in the units of kilogram per meter square second, and then you also have this Schmidt number of the liquid side. Okay, so in this case, only thing that we did not know in this problem is this diffusion coefficient that is also given it for you. So in solving this problem B, we are going to calculate the average liquid flow rates and gas flow rates at the top and the bottom and use them in the calculation of FG and FL. If I know FG, FL, I can calculate HTG and HTL, and then from there I can also calculate HTOG. So that's the strategy. Okay, so I'm going to solve it now in this page, and I want you to kind of follow this and make sure that you understand. This can be a little bit tricky. There are a lot of details involved. The first thing I will do is I will draw this schematic of the packet column. So here, this is a packet column, the counter current operating packet column. I'm going to use the same kind of notation we used in the packet column design, meaning the Y1s are here, Y2s are here. Okay, tray column we had something different. On the top you would say Y1 X naught, at the bottom you will say Yn plus 1 Xn. But here there's a packet column. I will use suffix 1 for the bottom and suffix 2 at the top. So now I'm going to mark all the values that I already know. For example, from the problem that we solved in the last class for the carbon disulfide, Y2 is 0.005. Capital Y2 is also 0.005. Y1 is 0.0658. Capital Y1 is 0.0704. X1 is 0.1 and capital X1 is 0.111. The X2 is 0. Please check these values, compare with your class notes in the last class, and make sure these numbers are okay. Fine? Okay. So we are going to do part B, which involves calculation of FG, FL, HTG, HTL, and HTOG. So we need to know all the flow rates. So from the previous problem, we have found that GS was given as 15.33 moles per second. If any of the value I write here are different from your notes, please raise alarm. Okay. Yeah. Correct? Good. Okay. If it's correct, you don't have to tell. If it's wrong, you tell. So first, I'll find G1. G1 is the molar flow rate at the bottom of the tower. Okay. So I get that as GS by 1 minus small y1. I know the value of y1. Okay. And if I do this, I'll get 16.41 mole per second. If you have a calculator or a phone, do this calculation and then keep following. Okay, there could be an error because I was solving this yesterday at 2 a.m. So I'm sure there'll be mistakes. So please be careful. So G2 is the gas phase flow rate at the top of the column. So that would be GS by 1 minus Y2. and this should be 15.40. So my average molar flow rate would be 15.91. So when I say average, I am talking about average of these two values. This is in molar flow rates. Now let's say I want to convert this into mass flow rate. So I need to multiply this by the molecular weight. And since the composition is changing at the bottom and the top, the average molecular weight of the gas will also change. So I'm going to calculate the molecular weight of the gas at the bottom as well as the top based on the composition. So I say Mg1. Okay. So this will be 0.0658. This is a mole fraction of carbon disulfide. And the carbon disulfide's molecular weight is 76.14. Plus the remaining is nitrogen. And the nitrogen molecular weight is 28. So you should get this as something like 31.16 gram per mole. And let's calculate the molecular weight, average molecular weight at the top of the column, where the composition of the solute is 0.005 and the rest is nitrogen. And you'll get 28.24. So G1 prime is G1 times Mg1. So now I got G1 prime as mass flow rate in gram per second, or you can write in kilogram per second also, 0.511 kilogram per second. Similarly, G2 prime is G2 times the molecular weight at the top of the column. So this is 15.4 times 28.24, and you'll get 0.435 kilogram per second. Make sure you get these numbers. So we have found the mass flow rate at the top, at the bottom of the tower, and then we'll get an average now from these two values. So G prime is the average of G1 prime plus G2 prime, and this should be 0.473 kg per second. Okay. Now I'm going to do the same thing for the liquid flow rate also. So first we'll do the LS value is obtained as 8.97 mole per second. Again, this is from the previous problem. L1 becomes 9.97. L2 is LS by 1 minus X2. X2 is 0 in this problem anyway. So, and then from here you can find L1 prime as L1, the molecular weight of the liquid at location 1. You see this molecular weight is obtained based on the composition of the liquid at the bottom. So at the bottom there's 10% of CS2 in the liquid, and the remaining 90% is the liquid. So this is the average molecular weight if you calculate that. Okay. I'm not showing that explicitly, but you can do this. So at the top of the tower, the liquid is fresh. It doesn't have any solute. So the molecular weight will be just the molecular weight of the oil, which is 180 here. Okay. So you'll get 1.615 kg per second. And then we can find the average mass flow rate as kg per second. So once you know these mass flow rates, you can convert them into English units. You can use this capacity factor from the chart, and then you can get the area, and from there you can get the diameter. So from here onwards, you know how to do this. So I assume that you know how to do this. So I'll directly give the value of the diameter of the column D comes out to be something like 2.27 feet, or approximately about 0.7 meter. Okay, so this is for you to check. So now we will go to the calculation of mass transfer coefficients. First, we will calculate Fg. So this is the expression for calculating the local mass transfer coefficient Fg. So we'll proceed first calculating this Skibin number, which is given as rho g by mu g dg. Rho g is something we obtained from the sorry, it's the other way around. So this is mu g by rho g. So viscosity is given in this problem. Rho g is something that we calculated in the previous problem itself. Yeah. Rho g by mu. It should be mu by rho. Please change if the question says so. It is mu by rho. So mu by rho is the kinematic viscosity divided by the mass diffusivity. So this is the correct expression. So rho g should be so the gas phase Schmidt number will be about 1.356. And then this G is the G average, but this should be given in the units of kilomole per meter square per second. We already know the molar flow rate, average molar flow rate, which is 15.91. You can see that we calculated here. So this is the molar flow rate average, 15.91. And this has to be divided by the area of the tower. So you'll get something like 41.34 times 10 power minus 3 kilomole per meter square second. And then the mass flux is the mass flow rate by the area. And epsilon L naught is epsilon minus 5 LT. This is 0.74. These values are given in the problem. So basically, if you look at this, we know all the quantities that we need. We know the Schmidt number. We know the molar flux. we know the ds parameter. So ds is this should be in the meters. It was given in centimeter, but you convert this into meter units. So now you know all the variables in this problem. So you can substitute for this and then get, it should be like this. If you substitute all this, you'll get Fg as something like 1.17 into 10 power minus 3 in the units of kilomole per meter square second. Now let's find out the liquid side mass transfer coefficient. The viscosity of the liquid was given in the problem itself. So it was given as 2 centipoise. I'm converting into kg per meter second. So it's 2 into 10 power minus 3 kg per meter second. Rho L is 810 kg per meter cube, also mentioned in the problem. DL is mentioned in the problem as well. So generally skipping number will be very large for the liquid, whereas for the gas it will be of the order of ones. But for the liquids, this would be of the order of thousands. Okay, so that's something you can cross check. And we need this L prime, which is the mass flux. This has to be divided by the area. And then you can substitute all these numbers and you'll get KL as 2.94 into 10 power minus 4 meter per second. Now the relationship between this small KL and FL is given by this. So FL is small KL times the concentration times the log mean difference of the composition of the B solvent free, the solute, the solvent. XB is solvent mole fractions. Okay, so C is rho L by ml average. So this is 810. The average liquid molecular weight is 174.8. And you should get something like 4.633 kilomole per meter cube. And XBM is x2 minus x1 over ln of sorry, this is actually with respect to component B. So we can write as 1 minus x2 so the log mean difference of concentration difference of component B can be written in terms of component A because the composition of solvent B at point 2 is 1 minus x2 and at that point 1 is 1 minus x1. So you know x1, x2 of the solute. So from here you can calculate x1, xb. Okay, so my suggestion is you continue this and get xbm and then c, and from here you can get fl. If you know fl, fg also is known, and then calculating htg is straightforward from here. Okay, so the values that you should get, fg was 1.17 into 10 power minus 3 kilomole per meter square second, and fl would be 1.3 into 10 power minus 3 kilomole per meter square second. So now htg is g average by fga. So g average is 41.34 into 10 power minus 3. Fg is 1.17 into 10 power minus 3, and A is 60 meters square per meter cube. So if you substitute all these things, you'll get this is something like 0.59 meter. And then HTL so HTOG we will calculate based on HTG plus 1 by A HTL. This value of A will be something like 1.306, and A is nothing but L average by M G average. So this is like 24.57 into 10 power minus 3. M is 0.455. That's the slope of the equilibrium line. And this will give you something like 1.306. So this is HTOG. You get something like 0.83 meters. So since the slope is about 0.455, the overall mass transfer is actually controlled by both liquid as well as gas. That's why if you see the height, the HTU for the gas is about 0.59, HTL is about 0.315. So both are kind of comparable and controlling. And the overall, suppose if you include both the effects together and then give one overall HTU, that would be about 0.83. Okay. So so that's it here. So what I've done, subsequently, which I could not cover because of all these mishaps, is that I would calculate NTOG from analytical expression and then also from graphical construction. Okay. So maybe in the next class I will follow that up. I will show you how numerically and graphically NTOG is calculated, as well as on the other part C. So we'll stop here.